Welcome. In this video I'm going to show you how you can perform a Freeman-Tukey-Read Goodness-of-Fit test using R and not using any libraries except perhaps the default ones. The R version that I'm currently using is 4.3 and these are the default packages that come with R. I'm using Jupyter Lab, but all of this should also work with, for example, R Studio, at least the codes. I'm going to explain how you can run this test without using my own library, stikpet R. I'll have a separate video if you want to use my library. I have a simple function for this. It's just going to focus on how to get the output and not if you should be using this test. It's actually a family of tests. You can set the weights and they should add up to something. But you can pick any weights you like, so it's a whole family of them. The example I'll be using is from the GSS 2012. I slightly adjusted it, so I'll download that and read it as a data frame. Then the only variable I'm going to be interested in is the marital status. I'm going to select it as my field, and to give you a quick impression, let's store the frequencies using the table function. So we want to see if any of these, if they could be all the same in the population. That's in essence what the test does. So I'm not going to be showing you my own library. I have a separate video on that. But without any libraries, I haven't found, I think, any other library that can do this. What we need is the number of categories, which can easily be obtained by using the length function. And then the sum function as well for the sample size. Once we have those, we also need to set our expected counts. We don't have any in particular, so simply going to use the sum of all counts divided by the number of categories. Repeat that k times, so we have 388.2 as expected count for each category. We then set the weights. The default is to use 4/3 and 8/3, so let's use that. And then this is the whole function, or actually formula, for this Freeman-Tukey-Read. As you can see, it's summing over from 1 to k, so 1 to k, so that's where this comes in. And then it's going to actually do another sum from 0 to x. So in this case, I call that j equals 1 to, and then the length of how long that j actually is. So basically for each weight, you do the weight multiplied by the square root out of the observed count divided by the expected count. So that's over here. You're taking the square root of that, which is the same as taking it to the power of a half. And then you raise that to the power of j, and because j actually starts here at 0, while in here I'm actually starting at 1, so it depends on if you start counting your arrays at 0 or 1, and r starts at 1. So that's why I'm subtracting 1 here. And then you multiply that result with the square root of the observed counts minus the square root of the expected count, and that result in itself squared. So that's what this one is doing, and that's adding it to the previous result. Alright, so that should give us the final result of the chi-square value. The degrees of freedom is fairly straightforward. It's the number of categories minus 1. And then we can determine the p-value, the significance, if you will, using the p chi-square function. So, and I'm going to say lower tail equals false, so it gives me the upper tail immediately. And this is extremely low, so usually we would then reject the assumptions that all frequencies are the same in the population, and they are significantly not. So there are also some corrections, one from Pearson, E.S. Pearson, not Carl Pearson. It's simply to multiply the result, the chi-square value, with the sample size minus 1 over the sample size. Williams has a slightly more complex one, but actually it's not that hard. It's just 1 plus, and then numerator, the number of categories squared minus 1 over 6 times the sample size and the degrees of freedom. So we have everything we need for those, so we can simply recalculate those chi-square values. There's also an option with using a Yates correction that's sometimes only referred for 2 by 2 tables. If the observed count is greater than the expected count, you subtract a half. Otherwise, you add a half. Unless they're equal, then you just keep them the same. So that can be done with a simple for loop for each, if you like, and that gives you a slightly different chi-square value again. All right, I hope this video was helpful, and thank you for watching.